Imagine a liquid that refuses to stay in its glass. A liquid so slippery it ignores the laws of friction and literally walks up walls to escape its container. This isn't a sci-fi movie. It's the weird, cold world of superfluids. Specifically, liquid helium cooled to a hair above absolute zero. To see this magic, we have to go cold, really cold. At 2.17 Kelvin, known as the Lambda Point, liquid helium undergoes a midlife crisis. It transitions into helium-II. It loses all viscosity. No friction, no resistance.
Behind every question lies discovery. I'm Saluna, and this is SciCurious, where we uncover the science shaping our world.
This phenomenon shocked the world in 1937. Pyotr Kapitsa in Moscow and John F. Allen in Cambridge discovered it simultaneously. It defied classical physics so completely that it eventually earned Kapitsa a Nobel Prize. They realized this wasn't just a fluid, it was a new state of matter. To understand why, we look at Bose-Einstein condensates. At this temperature, atoms lose their individual identity. They stop bouncing off each other and overlap, acting as a single giant superatom. They move in perfect unison. This makes it a quantum beast. Because they move together, there is no internal friction to slow them down. It forms what's called a Rollin Film, a layer just 30 nanometers thick that coats every surface it touches. Because there's no friction, the fluid acts like a siphon on a molecular scale, pulling itself over the edges of the beaker. It also creates the fountain effect. Just a tiny bit of heat creates a pressure difference so strong. It shoots the liquid into the air. It's physics behaving like magic. But how can it be both fluid and superfluid? Tissa and Landau proposed the two-fluid model. Imagine two ghosts occupying the same space, a normal viscous fluid and a friction-free superfluid existing simultaneously. Things get even stranger when you spin it. If you rotate a bucket of normal water, it spins. A superfluid stays perfectly still until you spin it fast enough. Then it creates quantized vortices, tiny quantum tornadoes that carry the angular momentum. Richard Feynman helped explain this. The fluid can only rotate in these discrete, quantized packets. And finally, heat. In water, heat spreads out slowly. In a superfluid, heat moves as a wave, like sound. It's called second sound. You can literally hear the temperature changing as it ripples through the fluid. Today, we use these properties to cool the massive superconducting magnets in the Large Hadron Collider. It was also used in Gravity Probe B to test Einstein's theory of relativity, keeping gyroscopes stable in space. It even helps us understand the dense, friction-free interiors of neutron stars deep in the cosmos. So, if you had a liquid that could bypass gravity and friction, what would you use it for? Let us know in the comments.
There's always more to discover. I'm Selu, and this has been SciCurious. Stay curious, and I'll see you in the next wonder.